Okay, so in this lesson we're going to discuss the substitution method, and we want to apply it to calculus problems, specifically integrals. But before we do that, I just want to take a moment to go back and look at how the substitution method is used in other areas of mathematics and why we use it when doing integrals. The purpose of the substitution method is to replace an existing variable or expression with another one, and we do this for the reason of simplifying a complex problem so that we can use the methods we've already learned when we're solving. So in our first example, systems of equations, we have here an example where there are two equations. Each equation has two variables, and we say we don't know how to solve two equations with two variables. We know how to solve one equation with one variable. So what we do in an Algebra 1 course is we say anywhere we see y, since it is equal to x squared plus 2, we can replace that y with x squared plus 2. And when we do this, it changes it from an equation with two variables to an equation with one variable, which is what we know how to solve. So let's rewrite this second equation. This would then become negative 2x plus 2. Now we're replacing the y with x squared plus 2 equals 16. So this is the substitution step. After that, we want to simplify. And since we see this as a quadratic, let's get 0 on one side. And now we can apply factoring to it, and we can solve for the x variable. So we see that in this problem, we started out with two variables. We said, let's use substitution to reduce it to one variable, and we were able to solve for it. Now, if we wanted to, we can take these solutions and we can plug them back in to find out what y is equal to for each case, and that would be how we used substitution in an algebra problem. Another type of problem that we can see substitution used in is solving polynomial equations that are not linear, not quadratic, but higher powers. And we see in this example, it is a 6th degree polynomial. And we say, well, we know how to factor things that are squared, but a 6th degree polynomial, that seems difficult. Well, you'll notice here we say, what if we perform a substitution? What if we let x cubed be equal to z? If x cubed is equal to z, then z squared would be equal to x to the 6th. And we can replace x to the 6th then with z squared, and we can replace x cubed with z. And when we do this, the equation is then written as z squared minus 3z minus 10 equals 0. And we say, hey, we know how to solve this. This is something we've seen before. And that's the theme of this lesson. We use substitution to take something that is complicated and reduce it to a problem that we're familiar with, and we use the existing techniques. So let's work this out. The factors here, z minus 5 times z plus 2 is equal to 0. We have z is equal to 5, and z is equal to negative 2. However, we have to recall that this problem was not given to us with z variables. We want to solve for x, not z. So we said, well, if z is equal to x cubed and z is equal to 5, we're using substitution again. This is called back substitution. We can take this 5 and plug it back into here and say that 5 is equal to x cubed, or negative 2 is equal to x cubed, and we get our solutions. X is equal to the cubed root of 5, or x is equal to the cubed root of negative 2. So again, we took a 6-degree polynomial. We said we don't have techniques for solving 6-degree polynomials by factoring, but we could change that polynomial to a quadratic, and now we're using existing tools, existing techniques that we know. So now let's consider an integral that is solved using substitution. All of the integrals we have used so far have had a function whose derivative was 1. Well, in this case, we see that x squared plus 1 does not have a derivative that is 1. Instead, its derivative is 2x. And now, when we see that the derivative is not 1, we cannot just use the power rule like we've used before. An additional thing that we see here is we have the multiplication of two functions. We haven't seen that yet before. So substitution for integrals is going to let us take this complicated integral and reduce it to a simple one that we know how to solve. So we start by saying let u equal x squared plus 1. Then the derivative of u is equal to 2x dx. Now, if you remember when we did the second fundamental theorem of calculus, where we were taking derivatives of integrals, we had to replace the temporary variable dt with the dx version. So we're doing that here again. We're saying that we have an integral that is currently in the form of dx, but we want to change it to the form of du. So we're going to have to complete the substitution in two ways. So let's look at this substitution process a little further. We're replacing x squared plus 1 with u. And we said that the derivative of x squared plus 1 is 2x dx. So this example is an even exchange. No adjustment necessary. We say I have a 2x and I have a dx. I can replace that 2x dx with du. So this problem can be rewritten as u to the 4th du. Again, just for emphasis, the 2x dx is now replaced with du. And the x squared plus 1 is replaced with u. The exponent of 4 is the exponent of u now. Can you solve this integral, u to the 4th du? Of course we can. This is the simplest example that we started this antiderivative unit with. It is a simple case of the power rule, and we say, great, this is going to be 1/5 u to the 5th plus c. But just like our algebra example with factoring, was this question asked using the u variable? No. So we have to replace u with what it is equal to. And we see that u is equal to x squared plus 1. So our final step is 1/5 x squared plus 1 in parentheses to the 5th power plus c. And we can check this answer by taking the derivative of it, and you would find that the derivative using chain rule will give us back our initial problem.